Okay, hi everyone. My name is Dr. Rehan Shah. I'm a lecturer in mathematics and engineering education here in the School of Engineering and Material Science at Queen Mary University of London. I teach on most of our undergraduate and postgraduate applied mathematics modules, particularly for first and second year undergraduates. And I'm also involved in a lot of outreach activities for the school, which involves giving talks, sessions, masterclasses um, at different schools around our local area in partnership with our department. So I'm going to talk about a short snapshot of a talk that I have ended up giving at several schools. And this one I've titled The One with Three Problems and One Answer. So it's a slightly more mathematical problem solving based talk, which is in alignment with my interests and what some of our students have also found interesting from doing some of our mathematics modules. And the theme for this session is around mathematical curiosity. And I've put a question here you can see in my online whiteboard, which I hope to answer and hopefully give you a flavor of hopefully having answered by the end of this session, which is regarding the idea of which do you think is more important when solving a problem? Is it really the question or is it really the answer? Now, the the response to this question, if I had to use that word, would vary depending on when if it's a school student being asked this question, and if we have a student particularly doing an undergraduate program at university answering the question. Because as we move from school to university, the narrative for mathematical problem solving really changes. So in school, you might be used to thinking that the answer is one of the more important things because it's the final solution to a problem. Often in mathematics, it's one or multiple answers that we look for. It's the thing that carries the most marks and often has the greatest importance, is what is a common perception because school mathematics is designed that way. When we come to university, the narrative sort of flips, and it, as opposed to becoming about the answer, which is also important enough, it really becomes more about the question, the problem. And particularly when we talk about research in mathematics as well, it's more about what the research question or problem that we're trying to solve is. And that assumes far greater importance. But I want to show that to you. And the way I'm going to do that is by taking us through three seemingly unrelated mathematical problems drawn from different branches and areas of mathematics. And then we work through them and try and see what happens when we try to solve them. So I've got the first problem here. As you can see, it says from the diagram that we have, it says we have a piece of string and we're going to divide that into two parts. So there's a longer part and there's a shorter part. So we have a longer and a shorter part. And I've just labeled them lengths A and B for simplicity. In mathematics, we like to use a lot of symbols to help make our life a bit easier. And you can see that I'm going to go ahead with an assumption that the longer length of this string broken into two parts is going to be A, and we assume that A is therefore greater than B. And I also give you a further piece of information about this particular string and how it's been divided. We have this property that we need to be satisfied in this case, which is that the ratio of the whole length of the string divided by its longer length is equal to the ratio of its longer length divided by its shorter length. Now, I've deliberately written this in English at the moment because one of the important things that I get students to think about is to mathematize this statement, which is currently written in English language. What that means is converting it to an equivalent mathematical form so that we can actually do some algebra with it and actually try and solve for something interesting. So the first thing that we can do is we can just write the mathematical equivalent of this statement in terms of the symbols we've been given in this problem. So if we have the ratio of the whole length divided by the longer length, it should be fairly straightforward to see that the whole length of the string can be written as A plus B. I'm going to divide that by the longer length, and I need this ratio, which is simply the division of the two quantities there, the ratio of the two lengths, is equal to the longer part divided by the shorter part. So we have A plus B over A equals A over B. This property holds. So this, whatever these two quantities are equal to, the expressions on the left and right side of the equal to sign, they are equal. And in mathematics, we also we like to reduce the number of symbols we actually deal with. So since this is a common ratio and they're both equal, I'm going to call it phi, which is a Greek letter. In mathematics, we use a lot of Greek symbols, and you'll get used to this when you come into university as well. So this is just a symbol. I could call it anything, but I'm going to call it the symbol phi. And what we can do here is, so this is a property we have. We have this particular ratio being satisfied. And our goal is to try here to see what we can do with this. So the first thing I can do is, particularly with the left side of this equation, a plus b over a, I can do a bit of a simplification on it. I can clear the fractions and I can rewrite it as 1 plus b over a. And if I want it to be even more, if I wanted to simplify this even further and rewrite it in terms of phi, because we know a over b is equal to phi, we can write this as 1 plus. Now, b over a is obviously going to be the reciprocal of phi. So it's going to be 1 divided by phi. Just write that clearly. 1 divided by phi. So at the moment, I have that if I just call this the left-hand side, LHS, of this equation, and I call this the right-hand side of the equation, then on the left-hand side, I now have 1 by 1 plus phi. And on the right-hand side, a over b is simply equal to phi. So what I've done here is we've gotten rid of the symbols a and b. We've reduced it to a single variable now, which we have as phi, which is also the ratio of the lengths that we talked about earlier. So now we have what we can see is an equation simply in one variable, phi. Now, when we have an equation and we have a variable, or rather an unknown quantity, the best thing we can do is to try to solve for this. If we solve for phi here, we will end up working out what the value of that ratio that divides a string into this specific sort of property actually equals. So we can do that. But before that, we need to first identify what type of equation this is so that we can apply the appropriate solution procedure. And it should be quite clear after a bit of mathematical rejigging. It's not immediately apparent, but this is the familiar quadratic equation, which you must have done in school at GCSE level when you have studied mathematics. So a quadratic equation, essentially, it doesn't quite look like a quadratic equation yet. So I can transform it to 1. I can just take this equation and multiply both sides by phi. So I'm multiplying on phi both sides to get a square term, which would make it more alike to a quadratic equation. So now I get phi square. If I take this right term and move it, and over here I will get phi plus 1. And to make it look even more familiar, like a quadratic, I can take all the terms to the left-hand side of this equation and set the right side to 0. And this looks much more like a quadratic equation in phi, in one variable phi. So the familiar form of the quadratic equation in general, you might remember if I write it in this notation, ax squared plus bx plus c equals 0 is what we're trying to match. A, b, and c here are the coefficients preceding the variable. So in this case, we can see that a is equal to 1, b is equal to minus 1 because we actually have a negative sign there, and c is equal to negative 1 as well. And most of you by now will probably be familiar with how to solve such an equation when it's in the form ax squared plus bx plus c. So if I want to solve for that equation, the general formula for the quadratic, if it's in this form here, for x, I would have got minus b plus or minus root of b squared minus 4ac divided by 2a, where a, b, and c can take the specific values for the equation that we want to solve for. So what that makes this, in this scenario, if we apply that solution for a quadratic equation, we would be solving for phi. And we can see through the plus and minus signs that we're going to get two values of phi coming out from this, just as we would have two values for x, because a quadratic will give us two solutions. So when we solve for phi, in this case, once we plug in the values of a, b, and c that we have here, we should end up, after some mathematical simplification, to something that looks like this. And if I just write that a bit nicely, we get two solutions. One of them, so I'm going to call it phi 1, is 1 plus root of 5 by 2. Whatever that is, we can work out a decimal value for that as well. And phi 2 is 1 minus the root of 5 by 2. Let's just write down what the decimal value of this is. So this one comes out to something that it just goes on. It's a bit of an ugly decimal, but something like 1.61803, square root of 5 being just over 2. Since the square root of 5 is slightly bigger than 2, we can already see, I'm not going to write down what this value is going to be, but I can clearly see that it's going to be negative because it's going to be bigger. The root 5 is going to be bigger than 1, so I'm going to get a negative value. Now, I've deliberately not written the value of that negative solution because we've got to ask ourselves that mathematically, we have two solutions to this equation for phi, and if we were just solving a pure mathematics problem, that would certainly be, both of the solutions would be acceptable and we would report both of them. But if we go back to the context of this question and remind ourselves what phi really represented, we might remember that it was a ratio of lengths. And in this case, we were talking about lengths of strings. Now, you might know from a physical geometrical point of view that lengths can't be negative. And so the ratio of the lengths also can't be negative. And that is what phi represents here. So we can't really have a negative solution for phi in this problem or in the context of this problem. So I'm going to discard the negative solution. So the only value of phi that we will hold on to as the solution for this problem is going to be this decimal value of 1.61803, which really, just rounding it off and understanding what it implies, it really means physically that 1.61803, the value for phi that we found, is the exact specific ratio with which I must divide this piece of string into two parts if I wish the whole part divided by the longer length to be equal to the longer part divided by the shorter part, or rather that ratio must be equal to this for this property to hold. No other division of the string into any two parts will provide us with this property to be satisfied. So that's quite an interesting result to see that there is something quite special about the way that we've divided our piece of string to get this property to hold. So that's the end of problem 1. We'll pause on that and move to a different problem, and just keep in mind everything that we've done up to this point. So I'm going to move over to a different problem. I've called it problem 2. And this is a completely different problem. You can see I've written some sort of sequence of numbers, and you can see they start with 1, 1, 2, 3, 5, 8, 13, 21. If you think about this, most of you might have seen such a sequence of numbers, and it might look familiar. And I've asked the question, what is this? And most of you will have encountered it at different points in your school mathematics curriculum, and will probably recognize this as the very famous Fibonacci sequence. And what's special about this sequence is that every term in this sequence, so if I look at every subsequent term, or for example, if I leave the first two terms as they are, for example, and take the term 2, I can see that the sum of the previous two terms, so 1 plus 1, ended up giving me 2. The way I generate the term after that is I take and sum up the previous two terms before the next term, which is 3. So 1 plus 2 gives me 3. If I want to get the next term 5, I sum up 2 plus 3, the two previous terms, and I get 5. And this property holds for all of the terms of this sequence, of course, which can keep going on to infinity. So the rationale behind the Fibonacci sequence is to get the next term in the sequence, you work out the sum of the two previous terms. And by definition, the first two terms of this sequence are defined to be 1. So we start with a 1 and a 1, and then we can work out all subsequent terms of this sequence after that. Now, that's the Fibonacci sequence. But what we're going to do to this is something a little more interesting. We're not going to really look at the terms of this sequence. We're again going to do something with ratios. We're going to take the ratio I've said of any term of this sequence with its previous term and write that out as a sequence of numbers. So if I start doing that, if I start by taking the second term, because that has a previous term, I can't take the first term because there is no previous term. So I start with the second term and I write its ratio with the previous term. So I'm just going to write it as a fraction. So that's 1 over 1. So for this term 1, I divide it by its previous term 1, and that's the value I get. The next ratio in this sequence is going to be when I divide 2, which is the next term, by its previous term, which is 1 as well. So 2 over 1. I can do the same thing. I get 3 over 2, 5 over 3, 8 over 5, 13 over 8. And let me do one more, which is 21 by 13, covering all the numbers that we have listed currently. If I now write this, because we don't like looking at fractions and it makes it harder to make sense of what's happening, we can rewrite this after a bit of simplification. So 1 over 1 just gives me 1. 2 over 1 is 2. then I get a 1.5, and I start working out some decimal values of all these remaining fractions. So I get 1.6 exactly, 1.625, and we start noticing something quite interesting. And I can do it so on and so forth. But what we can see here is that this sequence of ratios. So this is now a sequence. This new thing that I've got here is a sequence of those ratios of a current term with relation to the previous term of the Fibonacci sequence. So I've got 1, 2, 1.5, 1.66 recurring, 1.6, 1.625. So what I can start to see is that it looks like it's increasing, but then the sequence starts decreasing. Then it increases again, but not quite so much as its first increase. It doesn't exceed that value of 2 that it increased to earlier. Then it decreases, but not quite so much as 1.5, goes back down to 1.6, goes slightly higher up, again, not so much. So what we can see is certain things. So there is some sort of oscillation taking place in this sequence, which means the terms keep increasing and decreasing. But more interestingly, that oscillation doesn't take place with the same amount of increase and decrease. It actually starts decreasing the amount of increase or decrease. Rather, what is tending to happen is that we can see that it's getting closer and closer to some sort of value in the vicinity of the 1.6 decimal region. And we don't know what that value is, but we can try to see where that's going to tend to if we start taking more and more terms of this sequence. So the best way to make sense of this is to plot what we have on a graph. So I've done that here. So if we look at the sequence of ratios, so I've got on my x-axis of the graph, I'm going to list the current term that I use from the Fibonacci sequence, whose ratio I took with the previous term. So that's the current. So these are all the terms of the Fibonacci sequence, 1, 1, 2, 3, exactly as was listed in the original sequence. And on the y-axis, we've got the ratios that we got when we divided this current term by its previous term. So for example, we obviously couldn't do it for the first term, so we leave that term as it is. But if we look at the second term 1, when we divide it and got its ratio, we also got a 1. So I've put a dot over there, aligning it with a 1 on the y-axis. If I do it with 2, we got 2 as well. When I did it with the term 3 and did 3 divided by 2, I got 1.5. And so on and so forth, where we can see that what I ended up with. So if I start joining the dots, I'll start to see that this sequence of ratios started increasing. Then it decreased. Then it increased a bit. Then it decreased, but slightly, and then so on and so forth, where we can see that it's actually starting to taper down and assume some sort of constant value that it's converging to. It's increasing, decreasing, but the amount it's doing is small enough such that after a point, if I keep taking this ratio of terms all the way through to infinity, it's clearly going to start tapering down to a constant value, or a value that will vary by very negligible amount of decimal places, because it'll start fine-tuning itself such that it will not increase or decrease significantly. And if I were to write those ratios down, we would see here, for example, it was this was 1.6 recurring, this is 1.6, that's 1.625, that's 1.615. And if you ask yourself what you think this could tend to, clearly it looks like it's going to tend to something that's between 1.625 and 1.615. Interestingly, if you take this all the way through to infinity, you will find that it actually tends to that very magic number that we saw in problem 1, which was 1.61803. So what that really means is that as you take the ratio of any term of this Fibonacci all the way through to keep going towards infinity with its previous term, you will start getting a ratio of values of this sequence that will ultimately start converging to 1.61803 and start varying very negligibly around that region, which was exactly the ratio that we had in the first problem, which had nothing to do with the second problem. It's a completely different problem. This is a geometrical physical problem coming from division of lengths of strings in a certain ratio. This is coming from a numerical standpoint, when we're looking at a numerical sequence of numbers and doing some sort of algebra around that, and then graphing the results and seeing that it's tending to that value. But clearly, there was something quite special about this value that we'll come to and try and make sense of. So that's the end of problem 2. And I'm going to end off with a final problem, which was problem 3. Now, this is a completely different problem. It's an algebraic problem. So we've seen a geometrical or physical problem. We've seen a slightly more numerical or computational problem. Now we're going to look at a slightly more algebra-heavy problem, which you also might have seen or been used to solving in mathematics at school. Maybe not something quite like this, which is something I'll go on to explain. So we have this, what we call a continued fraction. Now, most of you will have seen fractions in school, but you will have seen fractions in the form of finite fractions. So you might have seen something like something like that, or you might be asked to evaluate something like that, and you should be able to do it. A fraction that terminates, it doesn't go on. But what's interesting about this fraction is that we can see that I want to work out the value of this fraction. I've just called it capital A for answer, so that I know that that's the symbol I'll use for whatever the value I end up from this fraction. But what's interesting is that this fraction, the way it's generated, it's doing 1 plus 1 over 1 plus, and it's doing that all the way through to infinity. So there is no real endpoint for this, and I can only represent its continuity with a dot dot sort of symbolism. I can't really do anything more. It's not ending at a particular point. And the question now remains, how can I, if at all, solve for this continued fraction, and what will the value of this answer A be for this continued fraction? Now, it might seem like, oh, it's terminating to infinity and we can't just keep going, keep doing it term by term each time. And clearly that's not the way to solve this problem. But will it have a finite answer? Will it converge to something? And if so, how do we find it? That's the question we've got to answer. To try to solve this, we can try to look at the problem a bit differently. So I've rewritten the same sort of continued fraction on this line here, but I've asked a question here, 2 questions actually. First thing I've asked is, and it's probably useful when we do mathematical problem solving, if we, before jumping right to solving something, we start to try to see if we can simplify the problem. And the first sort of hint we can think about, if that were the word, for trying to solve this problem might be to look at, okay, we want to work out the value of capital A. We don't know what it is. We don't know how we're going to do it. But can we at least work out what it can't be? Can we work out a certain set of restrictions or a range of values that A can take, which will allow me to sort of fine tune and make sense of the result? And if we look at this continued fraction a little more in detail, we can clearly see it's got plus signs everywhere. We start with a 1 and then we're adding something to 1, and then we're adding something that is then a fraction that is smaller than 1 because it's doing 1 divided by some sort of stuff. Whatever that stuff is, I don't care. It's going to be of the form 1 by 1 plus something. Let me call that stuff. Now, from a little bit of ingenuity, we can think, we can sort of conclude that A, and A is equal to this entire thing. So A must clearly be bigger than 1 because I'm adding something to 1, and that something is of the form 1 over stuff. And there's no sort of negative sign. It's all just addition. So it clearly has to be bigger than 1. The second thing I can conclude is that, okay, if I'm adding something to 1, what I'm adding is actually most certainly lower than 1. Because it's a fraction, 1 divided by something. It cannot exceed 1. If it were to be exactly 1, then our stuff would simply have been 1. And I know that entire set of stuff cannot be 1 because, again, that's again got a fraction attached to it. It's of the form 1 by 1 plus or whatever it is. So clearly this entire, and I know that this 1 by 1 plus whatever that goes on, this is bigger than 1. And I'm taking 1 and dividing it by something bigger. You can take a couple of examples. If you divide 1 by a number that's bigger than, it's say 2 or 3 or even 3.5, you're clearly going to get something that's lower than 1. So clearly this entire result is lower than 1. And that's what we're adding to 1. If we're adding something that's smaller than 1 to 1, we can be assured that the answer cannot exceed 2. So that's really, out of all the possible values that capital A could take for this continued fraction, we've somehow concluded that its value must lie within the very narrow range of 1 to 2. So that's already tightened our bound and going to help us solve this problem now. Now, the way to try to think about how we might solve this is by thinking about this next question that I've posed here. That, okay, we have 1 plus 1 over some stuff, but what exactly is this equal to? We can start to see that there is some sort of pattern here. This thing that I'm dividing this 1 by also looks exactly like the original thing. It's got a 1 plus 1 over 1 plus 1 over. It looks exactly, in fact, like the original question that we had, which actually we can see must equal A because that's what we've called it. So interestingly, this entire thing must also equal A. The reason for that is A is equal to 1 plus 1 over something, and then that keeps tending to infinity. The same is true of this part at the bottom. It's 1 plus 1 over, and this also tends to infinity. There is no concept of infinity minus 1 or something like that, or the fact that you've omitted a term. When you go to infinity, it's large enough such that anything like infinity minus 1 does not make sense. So this entire thing is essentially also the same thing as capital A, because we're taking 1, we're adding to it something smaller than 1 all the way through to infinity. So if I were to rewrite that exactly as we just said it, this would now make this problem look much easier to solve. We've got an equation, and we've got a single equation in a variable A, which we want to solve for, because our goal is to solve for the value of A, which is the value of this continued fraction. Now, there's something quite startling here about this equation. In fact, if you notice, it looks very similar to the equation from problem 1. If you just replace A with phi, of course, that equation that we have there, phi is equal to 1 plus 1 over phi, is exactly the same equation as the one that we have here, which is A is 1 plus 1 over A. The only difference being that we've changed the symbol. So we don't really need to waste our time solving this because we've already done the hard work and solved it in problem 1. In fact, we know this is a quadratic equation. We know we can multiply both sides by the variable A to get it to look like a familiar quadratic equation, which would give us something like that. We would be able to rewrite it. And we can already, without doing all the hard work of solving the quadratic, because we've done it in problem 1, quite clearly see that A will be equal to 1 plus or minus the square root of 5 by 2. That same sort of solution that we had in problem 1. The same two solutions. But again, we've got to ask ourselves, mathematically, both these solutions would make sense. But in the context of the problem we have here, which is a continued fraction, and the fact that we already deduced that this value of A must lie between 1 and 2, which means it cannot be a negative value. We cannot choose the negative of this solution. So the only solution from this plus or minus case that we can take is the positive solution, which we already know is equal to 1.61803 for the positive. We exclude the negative because that value of A in this problem cannot be negative because we have A bounded between 1 and 2. And sure enough, this result is in fact bounded between 1 and 2. It's 1.61803, or, with a lot of other decimal places. But in fact, it's the exact same solution as we found in problem 2, which had nothing to do with problem 3, and problem 1, which on the face of it had nothing to do with it. But what we saw later is that both problems 1 and 3 resulted in the exact same equation at some point later on when we tried to solve it. And when you solve that, of course, the solution must be exactly the same. So what we've seen here, just to finally summarize, is 3 problems, 1 physical and geometrical, all about strings and dividing ratios of lengths. We worked out the solution that ratio must take. It was 1.61803. Then we talked about the Fibonacci sequence, and we worked out the ratio of any term of that sequence with a previous term and looked at where that sequence of numbers started converging, and that happened to be 1.61803. Then we took a third problem, which was entirely algebraic, all about continued fractions, this specific continued fraction, and we saw that the value of that continued fraction was exactly 1.61803. So what I want you to think about as I conclude this session is really thinking about, we had 3 seemingly unrelated questions or problems, all of which led to the exact same solution. There's nothing quite related between the problems on the face of it. They're from different areas of mathematics. They've got different elements to them, but they all led to the same answer. And going back to the main theme that I started off with, it should now hopefully become apparent that with the answer that we got, 1.61803, we could be solving any of these 3 problems, and the answer would not tell us much information at all. It is important to know the answer, but it's not as important as the question. It was really the question that we started asking at the beginning, whether it's about strings or Fibonacci sequences or continued fractions, that really talks about or helps us define and refine what the answer, or make sense of the answer in the context of the problem. So as we can see, it's clearly the case that in this case, the question assumes far more importance than the answer. The answer is useful, but it's only a byproduct of the question. Without the question, we cannot make sense of the answer, particularly for the range of problems that we had here. And for those of you who might be familiar with where this topic might have led to or what's so special about this number 1.61803, you might recognize it as the familiar golden ratio, which is a very beautiful number in mathematics. It's this sort of the golden ratio is defined by this fraction that we saw, 1 plus root 5 over 2, which has this sort of decimal value, which just keeps going on and on. But there's something very beautiful about it. It not only arises in the three problems I've shown here, it arises in symmetries in mathematics. It's to do with architecture. It arises in biology. It really governs how everything in the world is actually governed by this single ratio, which is something very special. And if you read more about it, you'd be intrigued to see where it can crop up in our everyday life. So that's where I'm going to leave you with, and hopefully you enjoy the session and keep solving mathematical problems, and good luck with everything. Thank you.